more. Okay, perfect. Yeah.
Yeah,
So as I was
cool.
saying,
Thank you.
perfect. Yeah, nice. So as I was saying before, today we're going to go through the GDS Factory training. So the GDS Factory training is available, and it's also linked in the GDS Factory documentation. So GDS Factory is a Python chip design automation tool. So it's, as far as I know, the only tool that can help you do design, verification, and validation. It's very strong on the design part, especially on the layout. And specifically, it's being used heavily for photonics, analog, quantum, and MEMS. Yeah, and I'm a photonics engineer, and I've been doing photonics chips for 15 years. And yeah, we created this library 5 years ago as an open source library. The main reason to make GDS Factory is that it's very fast and very easy to use. I used another open source tool for 7 years before making GDS Factory, and it was very slow. Like it was based on Python. It's a library called Ipkiss, but yeah, it's basically even slower than GDS Py. So GDS Factory is very fast because even though it's Python, we're using C++ for all the GDS manipulation. So reading and writing big GDS files can be 30 times faster than traditional Python tools. Flattening GDS is like 50 times. Compounding bounding box, calculating the bounding box of a component can be 200 times faster. And yeah, this is a project that has been grown over the last 5 years, and we reached over 1 million downloads. I think we are now hitting like 2 million downloads. 2 million over. I think it's around 1.5 or something. It's rounding to 2. Yeah, we have more than 50 contributors and more than 10 PDKs. So in the first tutorial, we're gonna make, so I will assume that you have downloaded this training. So you can download the training on your computer. You need to download Klayout. It will assume that you have Python installed. We recommend using Anaconda. You need at least 3.10 or 3.11. So I think if you have 3.9 or 3.12, it probably won't work. So make sure you have the right Python. I will also recommend that you install the Klayout macro. So if you open Klayout, I don't know if I have it open here. If you go to Tools, Manage Packages, you can download the GDS Factory package. You make the Klife package. In my case, I already have it installed. I could even update it. I don't think I have the latest version. But this will allow you to have integration. So whenever we do show, like I can do a very quick example here. So I'm just going to run GDS Factory. If I hit, like for example, if I run this notebook, I can do plot. It will show it in Klayout inside the browser, but I can also do c.show, and it will send it to Klayout. So if I open Klayout, you can see it here, and you can zoom in and out. You can turn off layers. So it has the interactive aspect. So I would recommend you to install Klayout as well and install this Klife macro. So the first thing we're going to create is going to show how to create a component. A component is a canvas where you can draw polygons and you can draw references to other cells. You can basically, it's kind of like your canvas, like you're a painter, and we're going to create some hello letters, and you can move, rotate the references, and you can define different types of polygons. You can use like a operation with polygons, like buffer it, like increase the size of the polygon, and you can basically add different polygons. We can basically see how this interacts. And at any time I'm doing the plot, it will basically write it to GDS. GDS is the graphical database systems, which is the standard format for making chips. And you can also, as I was saying, you can also do show. And then if I do show, I can also see it on Klayout, which is running on another window. So we can do Boolean operations like not. I think something we could also do, like together, like we can try to define a parametric cell. That may be also a good example. So I'm going to open here a Python terminal. I'm going to create an MCI. This is an interferometric structure. I'm going to delete this code, and I'm going to create. So the first thing I need to do is I need to import GDS Factory. Can everyone read, or do you guys need me to make it bigger? I have a big monitor, but I don't know. Okay, I'm guessing that's yes. And yeah, I hope everyone is there. Okay, yeah. So the component is basically the canvas. So in the canvas, I'm gonna paint references to other components. And something that the GDS Factory has is that it comes with a generic PDK. The generic PDK is a generic library. It's mostly, it has a lot of components that can be easy retargetable for any foundry. You can adapt the layers that these components use, or any width or length. For example, this is a 1x2 splitter. You can change any of the geometrical parameters of this component to adapt it to your foundry, because different foundries have different layers. In this case, I mean, the best thing I would recommend is like when you go through the documentation and then try to do the training. But before, I wanted to give an overview of what you can find in the documentation. The documentation has the introductory page where you have some links here. It has also getting started. Basically, it will teach you how to install it, how to install the layout. And if you are new to Python, I would recommend also to learn how some of the basic things we do in Python, like functions or classes, or what's a decorator. These are basically concepts that may be a bit more advanced for Python, but they're explained here. And if you're also new to Git, and if you want to contribute back, you will need Git. But if you only want to use it as a library, you can just pip install GDS Factory. You don't need to use Git. And then you can go through the layout training. So the layout training will start with very basic concepts, how to make a component. This is what we're going to be doing in the first part of the workshop. We will learn how to do component. We will also learn how to create references and ports. So references are basically, it's like a pointer in memory where you store the object one time in memory, and then you can refer it multiple times. So it's like you instance one. This cell it can be instanced many times, as I was showing here in this example. You can have a component, it can be made of multiple elements, and the component can be stored one time in memory, but you can have like references, like pointers to that object in memory. Or you can also have an array of references, which you can have thousands of paths. If you just tell, okay, this is one path, and this is my X spacing, and this is my Y spacing. So this is the reference and ports. I will also show how to add ports. And then we have, basically how to connect things together. You can go through this. There's a lot of content in this tutorial, so I will just go through it so we can actually do some circuits as we were supposed to do. We can also define the grid snapping, maybe a bit of more advanced. So GDS is basically snap to grid, so that's something you need to understand. So you have to make sure if your components are not snapping to grid, you have to make sure you basically bring all the points to the same grid to avoid gaps. Yeah, this may be a bit of a more advanced concept. Maybe we should move it more towards the end. But this is also how to extrude paths. And we have a geometry. So today for the training, I'm planning to do the short tutorial, which is what I was running before in the Jupyter Notebook. This is something that you can download as a Jupyter Notebook and then run it directly on your computer, or you can download the whole package here. So, any questions? I hear someone. I think there's someone with background noise. So yeah, let's close everything here and let's start to make a new component. I think that's a good way to learn how to use it. So the component, as I was saying, is the canvas. So I'm gonna do I'm gonna add a reference, and I'm gonna add a reference to a component. So the way to add a reference to add ref, I'm gonna add a reference to another component, and then I'm gonna just show it. And when I run this code, it will basically, it creates a component. The component is unnamed. And inside the component, we have a reference to another component that's basically from the generic PDK. This could be anything. It could be an MZI, it could be a L shape, it could be a C shape, it could be whatever you want. In this case, let's gonna do a MZI because it's kind of like an interesting filter. It's an optical filter. And so it will be like this. So you have a component, and then inside you have a reference. So the second thing I'm gonna do, I'm gonna add another one. For example, let's add a reference to a band. And then the band is basically connected. It doesn't have a placement information. So I'm gonna band connect. I'm gonna connect you can see it's already out. The auto completion already tells me, like, I'm gonna connect the port 01 of the band to this MZI port 02. So I'm gonna connect the band input to the output of the MZI. And it's basically, you see, now it's connected here. Like at the moment, we have a very simple component. We just create a component and add two references. So we have a MZI, and then we have the band. So now what we can do is that we can make a parametric component. So the way to create a parametric component is to create a function. So I'm going to create a function called MZI with band. And I'm going to return the MZI, the component here, return Z. And then I'm going to do, let's just put this into an if main statement. And then I'm going to run this. I'm going to get the same thing. So MZI with band. Something that you will see a lot in GDS Factory, we have this cell decorator. So this is basically, instead of getting a name, the problem with, if you don't add this, let me comment it. Every time you run, every time you run this function, it will basically need to compute the code. So you see one high. But if I run 2, it will basically run 2 times high. So it's running the same code twice. So the cell decorator does 2 things. It basically gives you automatic naming, and it will also increase the speed because it provides a cache. So if the component is already computed, the second time you won't see high. It only gives you 1 high. And this is very important if you start doing components that start to be slower. You only need to compute them once. And something you also get by using this is that you can actually automatically create names. Like, for example, this is MZI with band. There's no parameters. But you can start passing parameters. So, for example, let's put a radius 10 to the band, and let's pass it inside the band. Radius. And here I can do radius 10, or I can do 11. So here I'm going to have a name that depends on the input parameter. So the name will be uniquely defined by the parameters of the band. And you can do 10, you can do 100. This is going to change the band radius of the output band. So if you do 100, it's a very big radius. Okay, so now we have defined MZI with a band. The second thing we need to do is we need to add ports. Like if you want to interface with the outside wall, this component needs to have ports or pins. So you need to add a port. Let's put the one port at the input of the MZI. This will be 01 will be at the MZI port 01, and the port 02 will be at the pen port 02. And ports are something that doesn't really get inside the GDS. So if you want to see the ports, something you can run is you can do show ports equals true, or you can also do something like C print ports. It will automatically run the ports into like a table, so you can see them in a table. But I'm going to do both. I'm going to do show ports equals true, as well as print ports. And you can see whenever I do show ports equals true, there's something, it's a bit hard to see, maybe because it's a dark background, but you can see the O2 label here, and then you can also see a triangle coming out. So the triangle coming out is going to be at the input of the component and at the output. So this is the O1. It's you can also see, if you do a Control G in layout, you can also put like a marker. minus 10, 0, exactly there. This is the position of the center of the port. The orientation is 180 degrees, and it also has a layer. So now that we have ports, you can actually do a lot of things with this. You could do like circuit simulations on this. You could connect it to all components. Sorry, I didn't hear that. I think maybe someone said something, but I didn't hear. Yeah, you can also route it to grading couplers. For example, you can route to a fiber single. So basically, this is connecting the component that we had with some input and output optical antennas, basically. And I can remove the print ports. So yeah, we've already done our first component. Does anyone have any questions? Okay, yeah. If no one has any questions, we can continue to the next part. Are you guys trying to follow at the same time, or I don't know if this is also like the part of the layout tutorial? We can also continue with the next session. So the design rule checking, or we can also jump directly into like designing components. And yeah, it would be nice also to understand if most of the people are photonics engineer, I can do the photonic specific components. If not, we can try to keep it general. No questions? Okay, so I can continue. Yeah, here we were basically doing the same thing. We were creating components and connect them together. We can also run through this. These are basically adding kind of like polygons. Yeah, this is basically adding polygons, connecting them. You can move and rotate. Yeah, you can do labels. Yeah, you can move things by port. So it's basically, and the last part I wanted to show is you can also write it to GDS with the write GDS, but you can also write it to STL or Oasis. So if you write it to STL, you can actually 3D print the things that you do. And so yeah, this can be 3D printed. If you have a 3D printer, you can make your chips in 3D printed shapes. So, yeah. This is the last part of the layout tutorial. We could cover a bit of DRC if you guys are interested. And if not, we can also go through any of the examples of circuits that we do. The DRC is basically using the K-layout engine. So in K-layout, you can run, we can create components, and then we can run DRC. So DRC, if you want to fabricate your chip at a factory, your chip needs to meet some manufacturing rules. Manufacturing rules can be things like minimum area of a particular polygon, minimum width, minimum space, or minimum separation between objects in different layers. There's also enclosure, or there's other more complicated rules, but these are the basic ones. So every layer that you manufacture, like for example, we can add some examples here, and then you will see we can make some example that has some errors. So this one, you can see the different different layers. So each of these, it will be, for example, the Vega layer is on silicon. Then you have different metals, can be at different levels on the stack. So it's kind of like a skyscraper. You can think of every layer will be like a floor of the skyscraper. And you need to make sure like things line up, like the pipes of the skyscraper line between the floors. Like if you're connecting different levels of metal, you need to make sure both metals are connecting with the pipe. This is kind of like the vias. We can also do connectivity checks, but yeah. So you will see, like, you can run K-layout, for example, like, if I run tool DRC, you will see, for example, like, let me bring it back. Let me close this window. If you go tools, DRC, I can just run the DRC here. So I'm just running some DRC that we just defined. So DRC stands for design rule checking. So I can go through the errors. And it basically will guide you through the errors. So I have 2 errors of minimum width. And then you can even show in red, like, what are the errors. So if the minimum width, we define it as 0.2 microns, you can see this component, this particular polygon has 0.1 micron. So that's a violation. Minimum space, 0.2. How much is here? 0.1. So it's also another violation. Minimum header to M1, 1 micron. How much do we have? We also have 0.1. So that's another error. Minimum area, it's also violating, like, minimum area. I don't know what was the number we wrote. The minimum area that we put, yeah, the minimum area was 0.05 micron square. So we have 0.01 square. It will be, yeah, it's violating too. And we can also make sure that the eyes need to be inside another layer. So these are kind of like some examples on how to run DRC, write your DRC tag, and run DRC from K-layout. Any question there before we go?
Yeah, we have some questions from our audience here. So one of them asks, how can we run circuit simulation? Is it importing the GDS file into numerical? And the same person also asks if it's possible to import the DRC rule from Foundry PDK.
Let's start with the first one first. So yeah, for circuit simulations, we have multiple options. And this is one of the nice things of GDS Factory being an open source framework where we support multiple tools. Because in the end, like, most of the tool vendors, they only try to advertise their own tools. But here, if you go to a particular, for example, like device simulator, we have multiple options or multiple tools. If you go to finite difference time domain, which is what calculates the S parameters, we have also like 4 tools. For circuit simulators, you were mentioning like interconnect. Interconnect is the numerical circuit simulator. Today we will be doing them with a different tool called SAX. But yes, you can basically export from GDS Factory to numerical interconnect, and then you can run your S parameters. For those who are not familiar with S parameters, in RF and photonics, your component can be described as a S matrix, like a matrix multiplication. So you have input fields and output fields. And for example, you have a matrix that tells you what's the relationship between the output field versus the input field. So for example, if I want to compute B1, I can get the S. So it will basically come in from the multiplication of the input field by the reflection. So if you have a reflection of 10% and then you put one here, you will get basically a 10% reflection. You can also measure transmission, which is basically S21 or S12. Most of them are reciprocal devices. So what we will be doing today, we will be using SAX, which is an open source circuit simulator. And that way, if someone doesn't have numerical license, you can still follow the workshop. Yeah, the second question, I think, was coming from the design rule checking. So I think the question is that, can we import your rules from the Foundry into GDS Factory? The question is, like, GDS Factory, it's basically like a design automation framework. Like, there is no input of DRC rules. Like, GDS Factory can help you write DRC rules, but GDS Factory only helps you write DRC rules in K-layout. Most of the foundries are that are giving these rules in a different proprietary tool called Caliber. So yeah, we can help you with that. Like if you want to get a Caliber rule deck, you have to either get one from the foundry or you have to write one yourself. But yeah, I don't know if that answers your question, but we can help you write the ERC deck as I did before, but it will write them in K layout. So they will only run in K layout. Does it answer your question? I don't know.
Yeah, and then Hollison also asked a question about running parallelized simulations on fully online environment like Colab. If there's any like ongoing efforts to improve heavy duty like running heavy duty simulations on just Colab without using something like Tidy 3D from Flex Compute.
Yeah, I mean, like for example, like as far as I know, all the open source, like Tidy3D is not open source. The open source like FTDZ or MIP could easily run on Colab because you can pip install them, and Tidy3D could run on Colab too because it's Python based, and the way it works is that you just buy credits and they will run it for you. So as long as you have credits and you have your key to send them simulation, it will still work. For FTDZ, which is the open source library that I can also show, I don't know if we have a link. If you go to the FTDD website, they have a Colab example, but we have examples here. The thing is that when you run this FTDZ that only works on GPU, you have to make sure you choose a GPU runner, because this is written in CUDA, so it requires a GPU. If you want to use another tool called MIP, which is the MIT open source library, this one will work in a CPU. It will work on your laptop. It's just that because it runs on CPU, it's slower. But it's also a very general S parameter solver. And the S parameter will basically compute the S matrix. For example, let's look at one of these examples here with Tidy3D. For example, if you have a component, you can excite it from all the ports, and then you will get the S parameters, which is basically the relationship from input to output. Like for example, let's look at a coupler. You can see like we have a good example here. Maybe a splitter will be good. You can see how automatically from GDS Factory, without having you to write draw in any CAD software external to GDS Factory, you can automatically drive the simulations. I think that's a very good advantage because a lot of times there's a lot of information that can get lost. For example, this is what the example I was looking for. This is a 50% splitter. So you put light here, 100% of the power here, 50% will go at the top, 50% at the bottom, which in dBs is 3 dB. So you get 3 dB S12, 3 dB S13. And you can also see the reflection. The reflection is like 40 dB. So it's it's very weak power, like going back. You can see here like there's different examples, but yeah, the advantage of using the plugin from GDS Factory is that you don't have to draw the component twice, and you can drive the simulation directly from GDS Factory. And it can be like things like antennas, things like couplers that I was showing. We have many examples that maybe it's not exactly the example you need, but I think it should be good enough for you to get inspiration on how to make it for your particular use case. Any more question? I think did it answer the question? Okay, I guess that's a yes. I don't know if you guys are there. Okay, let me continue then. Okay, so now that we run DRC, we're gonna run a finite element mode solver. So there's two kinds of mode solver. So there's finite element, and this is using an open source tool called Femwell. I haven't tried this example in a while, so I hope it works. But we will see. It's like live demos are always exciting because you know these things work. We have tests for all these components, so I think that should be good. So we are basically computing electromagnetic modes in a dielectric waveguide. So the first thing this is doing is basically meshing a component, and it's computing the modes that this waveguide can propagate. So if you're doing photonics engineer, a mode solver is one of the best tools that you can use to learn what modes can your waveguide support. Like still meshing. So this is basically directly from the cross section of the waveguide. It's basically computing the electromagnetic modes, and then we will be able to plot them. And like if we go back to the tutorial, back in the tutorial, yeah, the GDS Factory training. So yeah, this should be like the output of what you're getting. So you're getting some modes, and then it basically computes for different widths of the waveguide. You compute the effective index. This is basically the speed at which the phase propagates in your waveguide. Like a waveguide is basically like a pipe of light. And we're going to use two types. So we're going to use the finite element, which basically it has a. Maybe I should show like a mesh. Maybe we should show the mesh in the tutorial. But if you go to the plugins, we have another example of meshing that will basically explain how the meshing of an FEM example works. So basically a mesh will basically divide your structure into small triangles that you can basically adjust how fine you want the mesh to be. So you can do mesh refinement. So this is the FEM. On the other hand, we will also do a mode solver with the Tidy 3D mode solver. Even though the Tidy 3D X3D simulator is not open source, the mode solver is open source, so you can actually run locally. So this is different from FEM. FEM is, I don't know if you remember from the previous picture I was showing, it has, the meshing is done in triangles. This one is done in a grid, in a square grid. And you can also refine that square grid to be more finely meshed at the boundaries. When you compute the modes, the boundaries are very important to compute the mode correctly. Because if you see this index profile, like silicon is the yellow thing, which is high index material. This is basically very similar to an optical fiber. You have a core and a cladding. The cladding is silicon dioxide, so it's around 1.4 refractive index, but the core is around 3.4. So you have high confinement that the light basically stays here. Like the light will be basically going inside the screen and outside the screen in plane out of plane. And it's confined because of this high index material. You can see here this is the computer mode. So I think I already finished meshing. So we're gonna now show the modes, and you can see the modes a bit maybe small, but you can even compute what's the fraction, and we can also sweep the modes. Yeah, it's very fast. But yeah, these are basically computing the fine resolution modes for a waveguide width. We're sweeping the width of the waveguide. This is using the finite element mode solver. So it's running all these things that we run. In the end, we're going to see specifically this graph. So this tells you a lot of your waveguide. Like for example, like it tells you, for example, a lot of times if you want to guide light into the TE mode, you know that, for example, the first mode, the fundamental mode is TE polarized. And you can see it starts guiding as, even if with 250 micron width guide, but it's basically single mode in TE until roughly like 0.5. After 0.5, there's a second TE mode, and that starts to leave. So you have to make sure when you bend your wavegates, if most of the times you keep them in a single mode condition. That's why most of the photonic wavegates are on 0.5 micron wide. This is for the particular 220 nanometer thickness. But yeah, you can also see the second mode. The second mode is a TM mode. You can see the T fraction is pretty low. But as you can also see the mode hybridation. Like there's also a debunching of modes where you can convert power from one mode to another mode. This is still running. This is probably computing with a lot of it's computing a lot of modes for a lot of widths. Maybe I should just run it with less modes. Can also start running this one. But yeah, like so the plan that we're gonna do is we're gonna simulate the modes on FEM. We're gonna solve the modes on FDFD, and then we're gonna basically also we get exactly the same graph with a different method, and then we're gonna also compute group index and bend loss, and then we're gonna compute like coupling coefficients from one waveget to another, and then we will do like a thermal, basically a thermal phase shifter, where you can basically compute the thermal gradient of a tiny nitride heater, and then see how it changes the refractive index of your waveget as you apply a current. And yeah, and then we will do specifically a filter, that's an MTI filter that you can design to basically get some, you basically compute the S parameters of your component. So you can see your circuit, your interferometer. Every element can have an S parameter response. And then you can, as you change your circuit parameters, like the lengths of your filter, you will see how the spectrum changes. So if you have a delta length of 10, you get like 1, 0 on the spectrum. This is a filter that basically will block all the light going at this particular wavelength, like 1550. But you can you can double the length of the imbalance, and then you will get two basically wavelengths, two colors that will basically be suppressed by this filter. And the last thing we will do is basically a ring filter. So the ring filter, we will basically apply, this is basically a heater. So we apply some heat on top of the waveguide. So we contact the heat from the top. You will route this to a path. And then as you apply a current, the current will flow through this orange thing, and your waveguide will be under. And this is basically it's like a guitar. So the ring resonates at a particular wavelength or color, and by applying your thermal, you basically tune the guitar, and then you will be able to see some of the colors will be blocked and some of them will pass, depending on the heat that you apply. And then we will do a full chip with some rings and some interferometer filter that we did before. And this will be the end of the workshop. But yeah, I also noticed we're like almost like 20 minutes before the end. So let me see if you finish this part. If we can also start opening up for questions. Yeah, it's already finished. I just need to plot. Yeah, okay, here it is. So these are basically the the electromagnetic modes as a function of the width. You can see we're computing 4 modes, and we are computing the effective index of each of those modes. Any questions on FEM? Or now we can go to the next one. Okay, yeah, go to the next one. And yeah, we only have 15 minutes. So if you have any questions, don't wait till the last minute, because I need to run at 3. I mean, I think for you guys it's 45 p.m. I think most of you are in Illinois, but Okay, so I'm running the FTFD. So this is basically the tidy 3D mode solver. As I was saying before, the mode solver is open source, even though the FTDD solver, which is the most computational heavy, that's where they make the business. That's where it runs on the cloud, and you need to have credits. So here you can basically plot a particular field. I'm plotting the EX field, and then you can say what's the mode index. So this waveguides, as I was showing before, can support multiple modes. So every mode has an index starting at 0. And you can also plot mode index 1, which is the second mode. And this one is stronger on EY, so I'm plotting the EY. So it's basically orthogonal electric field to the other one. And this is the basically you can see the n effective. So this is the effective index at which the speed at which the phase moves. So you can see for the fundamental mode moves slower than the second mode. And this makes sense because the fundamental mode is more confined into the silicon. So it's slower when it travels. This one is less confined. You can see there's more light in the boundaries. So there's more light going through the oxide. And the oxide has lower refractive index than the silicon, so the light travels faster. So we can also compute for different waveguide geometries. You can also compute modes. So you can also create a slab where you basically have a slab of silicon instead of having fully etched. Like the first one we did is a fully etched waveguide. This is usually called strip waveguide. This is a rib waveguide where you only partially etch. And we can also do a nitride waveguide, for example. This is even less confined because the material of refractive index of nitrides is lower than silicon. So the index contrast is smaller. So the light, the mode is bigger. And we can do the same thing we did before. We can sweep the width of the waveguide and then compute the we're computing 4 modes. You can compute more modes. And I'm going to be plotting the effective refractive index of each of those modes as a function of the waveguide width. And then we also will show the T fraction. So this is the percentage of the light that is that has T polarization.
In the meantime, we have a question from one of our audience again. Is EO modulation, light doping simulation also available? So you have shown the thermal optic one. Is there a electro-optics example?
Yes, that's a good question. So, yeah, I mean, we have an example here on like it's not really electro-optical modulator. It's electro-optical. It's like a plasma dispersion. If you go to the device simulators, so we have an example with DevSim, and like this is basically a device simulator, like a TCAD, where you can compute the electrons and hole distributions as you apply a voltage. So this is basically as you apply a voltage, you can change your electrode and hole distribution, and because the electrons and holes have different refractive index, by applying a voltage, you can change the refractive index of your waveguide. So it's very similar to what I was showing with the thermal simulator, where by applying some heat, you change the refractive index of the waveguide. In the case of an electro-optic modulator, you are applying a voltage, and then you are changing the refractive index of the waveguide at a faster speed. These are in the order of thermal optic is basically in the order of kilohertz. With the electro-optic modulators, you can go up to gigahertz speeds. So it's much faster, but it's also a weaker effect. So the refractive index that you get, I don't know if you can see, but there's a lot of zeros here. We also there's a few GDS Factory developers. I know they're working also with trying to bring this into numerical simulation. So we don't have a numerical device simulator for like charge, but I know some people are working on it. For numerical, what we support is at the moment is basically only FTD and interconnect. Does that answer the question?
Yeah, and then one more question from a different member of the audience. A link is shown on the website featuring examples of with MEEP FDTD, but can't find it on the website. So maybe you can show where the MEEP FDTD example is.
Oh, sure. Yeah, we have two. We have this one that basically it takes a component and runs them on MEEP. So as I was saying before, you can just lay out the component once. So you can lay it out in GDS Factory, and then you can, if you import here I'm importing the MEEP plugin as gmeep, and then you can directly write as parameters of that component, tweak the margin of the simulation directly from your layout generator. So here are examples like this is a waveguide, this is the taper. I think this one may I will put more padding here, maybe a bit it's too close to the PML. So this simulation may need to be checked. But you can see a bend, for example. In MEEP, you can see the monitors are blue by default, and the sources are red. So here you can also put a source. You simulate the bend. So you can see a bend has 99% transmission. You also have some crossings. Also have low loss. And then we can also do multi-mode simulations. I think if you also want, you can also run them on multiple cores using MPI, or you can run them in batches. And there's also some examples with adjoint optimization. So these are the examples for using MEEP for like planar components, like integrated planar components. But you can also compute gratings. So this is out of plane diffractive element. So this is basically like an optical antenna. So as light comes in here, you see a grating for a particular wavelength. The light constructively interferes in a particular direction. That's why we have here the fiber. So you can see as a function of wavelength, for some particular wavelengths, they get diffracted out of plane like very efficiently, like maybe not very efficient, like minus 6 dB. So it's like 25% of the light will basically make it out. You can also make better grading if you design these things smartly. But these are the examples that we have here. But as I was saying before, these are just examples of what you can do with the tools. It's the same with the chips. We have examples of how to do like basic layouts. But the sky is the limit. As you become more familiar with the tool, you can start doing more advanced things. And if you want to contribute them back, you can share. If not, you can also keep them like private or for your research or for your work. I know most of you are doing PhD, but as you go into companies, you will be using also these tools to make your specific designs. So does that answer the question?
Yeah, I think that addresses the question. Yeah, thanks.
Thanks. Okay, we only have 5 minutes. If you have more questions, go ahead. If not, we can do a recap. I know most people wait till the last minute to ask the questions. So if not, can do a bit of a recap of what we've shown. they will have time to do the thermal or the filters. But what we've shown is how you install GDS Factory. So today we did a workshop. It's more of a hands-on doing things rather than a talk. If you want to also see the talk is also on the GDS Factory documentation. There's a YouTube link where there's a talk about GDS Factory capabilities. This talk is maybe a year old, I think, so things may have changed. Like maybe we add more things. I forgot where we are last year. But as an open source project, it's continuously evolving and improving. So yeah, maybe a year from now we even have better examples. Especially if people like yourself like use it for your work at the school, and they want to contribute. I think that's how the tool becomes better, by having more people contributing. So what we've done as part of the training is also linked on the documentation. So what we did is we download the notebooks. We basically we already installed GDS Factory with the plugins, and we also show how to install the layout macro. After that, we ran the layout tutorial, the short tutorial, where we created some polygons. We also created some parametric cells. We added ports. We also added references, and in the end, we added some Boolean operations. And then we finally write it into GDS, which is the format that you send the chips to the factory. And then we can also run them, save them as STL, which is the 3D format that you can fly through your component. And then we did some DRC checking to make sure the design passes the fabrication rules from the factory. And so we wrote some chip with some errors. Then we show it in layout, and we run the layout design rule checking, and then we found the errors. And it will be up to you to fix them. We didn't fix them here because the example here mostly to show how to find errors. And after that, we computed the electromagnetic modes supported in a waveguide thanks to the open source package Felwell. And we also did the same thing with another solver called Tidy3D, it's the FTFT solver. And then we did the same thing, computed electromagnetic modes. We wanted to do some thermal simulations, but we didn't have enough time. But yeah, you guys can run through this together. So in the end, it will compute like as a function of current, how much phase shift you get. And if you also have, if you want to get more advanced with the training, you can also design your filter. This will basically use the circuit simulator that I think someone was asking about circuit simulations. So yeah, if you have all these elements, you have an ACE matrix, you can basically, it's almost like solving the matrix. It's like multiplying the matrix to see how much field you get at the output as a function of the input. It's a transmission coefficient. So you can see as you change circuit, the different unbalance of the Mach sender creates different like wavelengths that the light gets blocked. And then yeah, the ring is also something that you can run on your own. But okay, yeah, we have 2 more minutes. Any last question?
Yeah, I have a question. So is there any ongoing effort to incorporate optical proximity correction by any chance?
I mean, I don't know what people are going to contribute. Like,
okay.
like it's a bit of with an open source project. It's a bit of like, yeah. I don't know what's gonna be contributed next year. If you look at what the direction is going towards, it seems like we're going more towards schematic driven layout and like more of a circuit simulations and more complex circuits. But if you want to kind of, if someone wants to work on a particular optical proximity, like mask compensation, you can always try to make it a separate repository, or you can try to contribute it back to GDS Factory or the plugins. Maybe that would be more of a plugin. Something we did over the last year is that before, all these plugins used to be part of GDS Factory, but we've seen that as we create more and more interfaces with the tool, it became a bit, maybe too much code to put on the same repository. So we made separate codes. So we moved the code out. So.
I see. That makes a lot of sense. Thanks.
Yeah. Any more questions?
Mustafa just asked, is there a way or built-in function to create a path with a certain length between two given ports?
Oh yeah, that's a very good question. Yeah, if you go to the layout tutorial, it's if you go to the routing, we have routing with path length match. So all these routes, you can get single route. So we have get route, which does a single route between two ports. But we also have get bundle. Get bundle will basically bundle a list of ports in the same orientation with another list of ports. So what you're asking is basically a get bundle or get path or get route with path length match. So we have some example here. If we go a bit further, get bundle path length match, or even the get bundle itself also allows you to, if you define, I want path length matching, and I want to basically add an extra length. So this is basically connecting this list of ports with another list of ports. And I don't know if you noticed, but here there's a little loop. So depending on the length, the length difference between these wavegates, you basically make the loop bigger or smaller. You can see here maybe more obvious. So here, these ones are very close. This port, let me put a pointer here so we can know what we're talking. This port to this port, it's very close. So you have a lot of extra length. This port to this port is pretty far. So here, your little wiggly extra delay is at the minimum. So this is basically, it's called path length matching. So yes, path length matching is one of the nice features of the GDS Factory routers. Okay, perfect. So thank you very much. I don't know if I will get a recording, but if you guys want to post it on YouTube, let me know, and I will be able to put it on the GDS Factory documentation. That way, people who were not able to join today will be able to watch it here. And if you have any questions, feel free to make an issue on GitHub or try to also create a community around the university. And something we've seen that's very successful is that GDS Factory has kind of like communities in different universities, and we've seen universities doing self-organized workshops where people go with their computers and they spend like a day doing chips together. And so I think this is a very good way to kind of like meet people, learn from each other, and create like a small communities of chip designers in different schools. So I hope you guys enjoy the workshop, and you can also share some of the learnings with your lab mates and your other of your friends at school, and maybe see you some other conference. If not, I'll see you probably on GitHub.
All right, I think that concludes our workshop. Thanks, everyone.
Perfect. Thank you.